Now in this video, we're going to switch topics just a little bit, and this is going to be the beginning section for maybe, I don't know, 4 or 5 videos that we're going to do on multi-threading. Now they mention multi-threading in the objectives here, but historically they haven't gone too deeply into multi-threading on the exam. For one reason, multi-threading is extremely complex and is considered a considerably advanced topic. So you need to understand some basics about multi-threading, and I would strongly encourage you to go out and do some reading and some tinkering with multi-threading. Tinkering is a Southern technical term for practicing, because multi-threading is a part of our world now. Now keep in mind, until the mid-2000s, computing power was delivered by ever-increasingly powerful CPUs. Moore's Law stated that about every 18 months, the processing power doubled, and they've kept that up. It's actually gotten shorter. Now, the CPU, of course, is the central processing unit, or the processor. Now, most applications ran as single process applications, and they all utilized one thread of execution. Now, a thread is the smallest unit of execution that can be independently scheduled by the operating system and handed to the CPU for whatever processing needs to be done. So, in a single-threaded OS, the computer runs one application at a time, and one aspect of that application can run. And when the application needs to perform some intensive calculation, the computer appears to freeze because nothing else can happen while that one thread is running on the CPU and the calculations taking place. No other actions can be taken until that process running on that single thread is complete. Now this is what's called synchronous processing. One action at a time on a single thread, and we lived this way for quite a long time. Now, multi-thread provided relief to this situation because, just like our own brains, most of the time we're not using the CPU anywhere near its full potential. And so we could go out there and create multiple threads or spawn multiple threads and run different functionalities on those different threads. And the CPU would just switch back and forth between the thread. And so while we were multi-threading, we were not really running two things parallel. We were simply allowing the CPU to switch back and forth between these threads and execute different pieces of them. Now this is much like the way you and I organize and execute our daily responsibilities. We get up in the morning, we start answering email, we answer phone calls in the middle, we take a look at reports, whatever it is you do. But you don't just do one thing. You do 4 or 5 things at once, and you'll work on one for a minute and stop and talk to someone, work on another one to stop, take a phone call, that sort of thing. Now multiple threads can be handled in 2 different ways by the operating system. The first is collaboratively, and this is where every thread has to give up control so the other thread can execute. In other words, kind of like the threads themselves are giving up and trading out. Then there's preemptive multi-threading. This is where the operating system, or the OS, ensures that no thread monopolizes the CPU. And by the way, this is how the Windows operating system works. Now in .NET, just kind of a little glimpse of what's going on. All applications in .NET run on several threads. There's a garbage collector thread that is out there in the background. It is responsible for the garbage collection processes. There's a finalizer thread. Go back to the videos where we're talking about garbage collection, the finalizer, iDisposable, all that. All this is right there. The finalizer thread runs the finalize method of objects. The main thread is where our main application executes. The UI thread manages and updates the user interface, because in these object-oriented, object-driven user interfaces, there's a lot going on, but we still want to maintain very quick, responsive feedback to the user as they're clicking on buttons and choosing drop-down lists and so forth. Now, multi-threading, no doubt, makes applications feel a lot faster and a lot more responsive, and everybody likes that. However, multi-threading also can present a few disadvantages, and you need to consider these anytime you start to go down the multi-threading road. Each individual thread requires time to create and destroy memory for that thread, set up the processes for that thread, and so that's just pure overhead. Now, the context switching between threads, or the CPU switching back and forth between the threads, can consume considerable time and resources. So if you spawn too many threads, you're basically kind of shooting yourself in the foot, and your program's still going to be slow and kind of clunky. Keep in mind, it takes time for the CPU to schedule the threads, load them onto the processor, and every time it switches to another one, it has to store the current state for each time slice as it's moving back to another thread. Now, one other thing, you probably figured this out already. Multi-threading adds considerable complexity to the application development and runtime management of your applications. there has to be communication between the threads. Now, coordination between the threads' actions can get kind of tricky. One thread might need to wait for another to complete before continuing, and then later on it might need to just kind of bull on through and not have to wait. Now, since all threads in a process share the same resources in memory, you're going to have to write some code to make sure that the threads are not creating inconsistencies by accessing and changing each other's resources. So as you can see, multi-threading brings a lot of power and efficiency to our programs. They also bring quite a challenge to the developer. Microsoft's got some new ideas on that, and we'll take a look at these as we move through the next couple of videos.